Hey guys, welcome to part 2 of coding a chess engine in JavaScript. I'd like to cover some topics today that I didn't discuss fully in detail about my engine last time, and just list these off in case you want to implement your own engine. So the first one is I'll talk a bit more about alpha beta pruning. I'll talk about my implementation of a transposition table. I'll tell you about the nodes per second and optimizations I've done to the engine. I'll talk to you about more in depth about my evaluation functions. I'll tell you how I've made a longer table of book moves to improve the start of the game. Okay, so now I'll be explaining the alpha beta pruning algorithm in a bit more detail than what I did last time. So essentially it's a way you can search less than the full tree of nodes while still getting the same result as if you did. And sometimes this can be a dramatic improvement, sometimes it's a small improvement. And there's ways we can optimize it, so it will be more likely we can prune more nodes. But in general, it works by finding out if a node doesn't affect the outcome of the top node by seeing if it's already had a previous node that would make it worse no matter what the node was. Now I'll explain it using this example of this tree here. So you start off as you normally would, going down to this node here, the 5, and this is the minimizing player, so out of 5 or 6 it's going to pick 5, and now here we've got the maximizing player, which will pick the max of this branch or this branch. So here it will pick the max, and this player here on the right branch, that will pick the minimum. So here the first value is a 7, and nothing's normal, so that would make this a 7. But then when we know that this is a 4, we know that this must be less than 4, because if this is larger than 4, this will stay as it is. If this branch here is less than 4, then this will become whatever that branch is, and that will be less than 4. So we know that regardless of this branch, the AI will definitely pick the left branch here, which will be a 5. Using the same logic, we've got the minimizing player here, and it goes all the way down to 3, and we don't get to prune anything on this branch. Here we've got the maximizing player, which wants a 6. And here we can do the same thing. The minimum of 6 is 6. And here we get another 6. And we know it will pick the max here. And you know that this has to be less than 6. Less than or equal to 6. So it can just pick the first branch because it knows that it's going to be less than or equal to 6 either way on this branch here. Here there's going to be a 7. Here, this one we get to prune quite a bit, as you can see. Here we've got a 5. Here, which goes to a 5 here, which goes to a 5 here, and goes to a 5 here. But here, this is the maximizing player, okay? Which means it will pick the max of these 3 nodes, the 3, the 6, and the 5 here. But you can see here, this guy's the minimizing player. So he'll pick the less of these 2 nodes, which means this value here, even without calculating this whole branch over here, we know it's going to be less than or equal to 5, which means the AI would never go down this branch. And it would have to pick this middle one here, because that produces the highest value. So that's alpha beta pruning in a nutshell, and this can be implemented relatively easily in code. Okay, so now I'd like to talk about a thing called transposition tables, which are very vital for getting a larger depth of node search. So transposition tables store the position of a board along with its evaluation, so that way you don't have to search to as high of a depth to get all of the nodes searched in detail. So for example, if I play e4, e5, knight f3, knight f6, we get to this position here. Where on the other hand, if I go back a bit and we play knight f3, knight f6, then e4, then e5, we get to the same position, but we take a different order of moves. And currently in the function of Minimax, we evaluate both of those separately, which takes a huge amount of wasted time to think that we're doing the evaluation for both of these positions. And that gets even worse if we're doing moves after these positions at a larger depth. So what we can do instead is store a position of this in a large dictionary, where you have a hash of the position on the input, and then you get the output, which is the evaluation. Okay, so now I'd like to talk about the eval for the terminal nodes. So that's when the depth has reached 0 and it's done calculating, and it just wants to find the value of a position. So here, we can see I use this long, complicated line, where total white is the total value of white's position, total black is the total value of black's position, total white is the value of white's again, and total black value of black's. And black's position is going to be negative since their piece values are negative, and total white will be positive because their values are positive. So what you may think I just do is you may think that I just do simply return total white plus total black, which would give me the difference between their two positions, which is what I had originally. But what I found when doing this was the AI wouldn't try to do much. He'd just shuffle his pieces around without trying to make anything happen. Because if he's up by a couple points and his position's good, there's no real point to risk anything. So what I've done here is made it such that the AI has some incentive to do things. This is quite complicated. Like I've got 20 sets of brackets here, which is quite boring. But what essentially it's doing is, I'll simplify it down a bit. So essentially, if I get rid of all the math.round stuff, you're just returning the you return the normal eval times this number. I'll get to why this number is important later, but you're multiplying it by that number, and then you're dividing by this number here, which is simply the total value of all pieces, value of all pieces, plus that number there. Now these are, this here, if you look at it, we are essentially dividing this here, the normal evaluation divided by the value of all the pieces. So that means when there's fewer pieces, the evaluation will be worth more. And then these numbers here, let's say we didn't have that, this would be extremely harsh. We're just adding those numbers here makes it a bit softer. It kind of averages it out a bit, which is very useful for making it less harsh. Okay, so finally, I'm going to talk about my opening book table and how I've improved that to essentially cheat to make my chess engine good. So originally I started out with just having a hand-selected amount of book values. I think I had the fried liver included, and I think the Sicilian defense, which isn't a lot, but it gave my AI some sort of structure for a very, very limited number of openings. But what I've done now is I've given it a proper opening book. So how I've done that is here, there's these things called eco codes. So here that's an eco code, and it corresponds to an opening, and a list of moves which represents the game and how to get to that positioning. So here I've got two books here. One is here, and then one is here. So this one, they're in different formats, so I've had to do them slightly differently. So the start position here is nothing, and we've got the Barnes opening, the fried fox, just tons and tons. Like here, this book goes down forever. Like it's got some 20,000 lines in it. So then what I've done is I've used this Python script to convert all these eco codes to the fen positions that occur in those openings. So then I get this list of fen strings that occur in those openings. I've taken off the last two elements as they're not really valid for the evaluation of a position, and they don't particularly matter. So you've got en passant, castling, whose turn it is in a position. Here, that's the starting fen, and we've got about 10,000 different positions that it can evaluate. So then from here, I do fen to move.py, which is a Python script, which, ignore this, that's just some debugging stuff. But essentially, I write this file, which generates the fen string, then a book value. So that's the evaluation, that's the starting position, ending position, if it's a promotion piece, and the name of the book value. So it does all of that, and then I just kind of copy and pasted that into workers.js, and here you've got a huge amount of book values, which is very useful for the position. So I can use this to get a very good opening position against most players. and it can go very deep sometimes. You can sometimes get 10, 11, maybe even 12 moves off the opening if you play something like the Luyuro Petals.